osteology, we'll be discussing about the structure of bone, its chemical composition, various parts. We also have to look at the development of bone, that is the process of ossification, whether it is membranous ossification or endochondral ossification. First, we begin by looking at the basic structure of a long bone. Say, for example, the femur bone in the lower limb. We have got a diagram for that. Let us look at the diagram and discuss various parts of the adult long bone. In this diagram, we are looking at the femur bone. This is taken from the lower limb, the thigh bone. It's a long bone and typically having one shaft and multiple epiphyses at the ends. So as you can see, this is the shaft of the bone, the diaphysis. And if we are talking about the epiphysis are at the end of the bone, either end, like we can see. Plus, we have to understand that the diaphysis is only one in number, whereas when we are talking about the epiphysis, they can be multiple in number, either at this end or at the other end. Developmentally, the diaphysis is coming from the primary center of ossification. This center is actually appearing in the intrauterine life at around 6 to 8 weeks of intrauterine life and is going to form the shaft or diaphysis. And once the baby is born, after birth, we will see at the ends of the long bone, there will be the secondary center of ossification. And the secondary center of ossification can be multiple in number, forming multiple epiphyses. So as we are telling, it could be at this end or at the other end as well. And they are appearing after birth. And then we have to talk about this metaphysis region, one here and one at the other end. In fact, when there is the growth of the bone in the growing children, they'll be having a growth plate, and that growth plate helps in growing the length of the bone. Now that growth plate, as it changes into bone, it will be named as metaphysis. So the replacement of the growth plate is by metaphysis. Metaphysis is considered as the epiphyseal end of the diaphysis. May it be on this side or may it be on this side. So as we are mentioning, this is the region of growth plate which is later replaced by the metaphysis, and metaphysis is basically the epiphyseal end of the diaphysis. Means the shaft, when it is approaching the end of the bone, that is where you have the metaphysis. The shaft of the bone, when it is reaching the end of the bone, that epiphyseal end of the diaphysis is called metaphysis at either end. Now let us take a section of the bone and looking at the two types of bone. One which is on the outside, the cortical bone, and one on the inside, which is trabeculated or spongy bone, that we can see in the next diagram. As we notice in this section of the bone, there will be two type of bones. One which is towards the outside, the periphery, sheath-like, it is the compact bone, and the one which is towards the interior, towards the medullary cavity or towards the end of the bone is the spongy bone. So let us number them. Number one is the compact bone and number two, it is the spongy bone. Now it is understood that long bones, they will have one medullary cavity where we are having the bone marrow, and in this medullary cavity, the bone marrow in the beginning is red bone marrow, but later it is invaded by fatty tissue and it becomes yellow bone marrow. Now when we are looking at the medullary cavity which is to the interior of the bone, there we will have spongy bone and it is different from the compact bone. What you find is towards the exterior, like we see making the sheath of the bone, is the compact bone. As the name is suggesting, it is going to be hard and it is having dense arrangement. In fact, when we are looking through naked eyes, there will be no air spaces seen, which are evident in the spongy bone. If we are talking about the spongy bone, as the name is suggesting, it will have lot of spaces and is present in the epiphyseal region, but can extend into the diaphysis also if we are talking about the medullary cavity. Otherwise, it is at the ends of the bone, the epiphysis. So what is the structure of this spongy bone? If we are focusing upon that, we'll find the spongy bone is having lot of air spaces, and the basic structure is trabeculations, and those trabeculations, they are constituted by some rods, some plates, the spine-like process. So that is the basic structure of the trabeculated bone. Those trabeculations are constituting the spongy bone, which is at the epiphysis ends of the bone, also extending into the medullary cavity towards the interior of the long bones. The compact bone is in a cylindrical fashion, covering that spongy bone all around. As we talk about the structure of the compact bone, we'll find that it is having the structure made up of osteons. Osteons as seen in the compact bone. It is a laminated structure around the canal which is called as the Haversian canal. So we'll be looking at the structure, but when we are talking about the compact bone, it will have the osteons with some laminations and the Haversian canal. This osteon arrangement is absent in the spongy bone. Let us now discuss the process of bone formation, the ossification. And the ossification can be of two types. Mostly it is endochondral ossification, though there are some bones which will form in membrane, so membranous ossification. We will find that most of the bones are developing in the endochondral ossification. Say for example, the upper limb bone, lower limb bone, the sternum, the ribs and the vertebra, they're all developing in a cartilage model by the endochondral ossification. You can mention about that here. Chondro means cartilage, and in the beginning, embryologically, we'll have the mesenchyme. In the mesenchyme develops a cartilage model, the skeleton for the bone, and in the cartilage model, there'll be endochondral ossification to form the bones. But when it comes to the membranous ossification, like some bones in the skull cap and facial skeleton, bones like frontal bone, parietal bone, or most of the skeleton of the face, that is formed by the membranous ossification. Here what happens is, first you have got the mesenchyme, and in the mesenchyme there is no formation of any cartilage model. It becomes a membrane, and that membrane becomes the bone. That is why it is called as membranous ossification. Example we have mentioned the skull cap bone, like the frontal bone, parietal bone, which are covering the brain here, and then even the facial skeleton. But these kind of bones are very few in number. There is a third category of bone formation, that is basically a combination of the endochondral and membranous ossification. For example, if we are talking about the mandible bone or the clavicle bone, we say that they are developing in membranous ossification, though partly they are also having the endochondral ossification. So chondromembranous ossification for few bones like mandible bone, the clavicle bone. We are going to look at a diagram, a baby developing in the intrauterine life, and there we can discuss the types of ossification once again. The diagram is showing us the skull cap and the facial skeleton developing in the membrane, intramembranous ossification, whereas if we look at the base of the skull or the vertebra and the ribs, the upper limb bone, lower limb bone, they are basically developing from endochondral ossification. Let us mention the detail here. The intramembranous ossification is giving us the bones which are forming the roof of the skull and the facial skeleton, whereas if we are talking about the base of the skull, at the base of skull we have even the involvement of endochondral ossification. So here it is mentioned, chondro means cartilage, and there will be a cartilage model turning into bone, can be seen at the base of the skull and most of the bones in our body this way. For example, we are talking about the vertebra bone or maybe the ribs, the sternum, forming the bony skeleton for the thorax region, the abdomen region, or if we are talking about the upper limb bones or lower limb bones, we understand the limb bones are developing from mesenchyme, which changes into the cartilage model, which then ossifies. And since this is a baby in the intrauterine life, you can see only the shaft of the bone, the diaphysis, which come from the primary center of ossification. We have mentioned the primary center of ossification, which will contribute to the diaphysis of the bone, will be appearing in 6 to 8 weeks of intrauterine life. And here we cannot see the epiphysis, because epiphysis, which come from the secondary center of ossification and will be developing at the ends of the bone, will appear only after birth. So they are not evident here since the baby is still inside the uterus of the mother. Let us now look at some more details of the endochondral ossification. As we mentioned, if we are talking about the endochondral ossification, which is going to form most of the bones in our body, the term chondro means forms cartilage. And in the beginning, we have one cartilage model developing in the embryonic mesenchyme. As you can see, this is the developing baby, and there you have a hyaline cartilage model. So fetal cartilage is hyaline cartilage, and this cartilage has formed a model. There we will find develops one primary center of ossification. As you notice here, this primary center of ossification will be appearing in 6 to 8 week of intrauterine life. So here you mention 6 to 8 week of intrauterine life, the primary center of ossification is appearing, is going to form the shaft of the bone. As you can see, the diaphysis. So here, this primary center of ossification is going to form the shaft of the bone or the diaphysis of the bone, and the length of the bone keep becoming longer and longer. Now, as the baby is born, after birth, there will be appearance of secondary center of ossification as well. So here you find is shown the secondary center of ossification which will appear after birth is at the ends of the bone. It is seen each long bone has a growing end, and the appearance of the secondary center of ossification is variable. Like here, the secondary center of ossification is appearing at this end a bit later. So this is the other end having secondary center of ossification appearing a bit delayed. But these secondary centers, they are the one which are going to form the ends of the bone or the epiphysis. So as you see, the secondary center of ossification which appeared after birth is now forming the bone which is called as epiphysis. But then there is a gap between the epiphysis and the diaphysis. There you will have the growth plate which later will become metaphysis, and that growth plate is also called as epiphyseal plate. So as you notice, this epiphyseal plate, which is other name of the growth plate, is made up of hyaline cartilage. It is not yet ossified, and what we find is because of this growth plate, the length of the bone keep increasing. This growth plate will keep growing towards the end of the bone, and from below, part of the growth plate will be getting converted into the bony tissue. So that is how the bone is growing in length. It appears that growth plate keep moving higher and higher, and at one point of time, the growth of cartilage is slower than the growth of the bone. In that case, the growth plate will disappear and no more growth is possible. It is an adult bone. Instead of growth plate, now what we get is epiphyseal line. So in the adult, once the growth plate disappears, epiphyseal plate will become epiphyseal line, as is evident here. And this part of the bone where we used to have growth plate is then named as metaphysis. So metaphysis is the part of the bone which takes the place of growth plate. As the growth plate disappears, the bone which appears is named as metaphysis. So this is the region of metaphysis. Ultimately, we'll find all the hyaline cartilage which we started with has converted into bone gradually, but still there will be some hyaline cartilage which is always persisting at the ends of the adult bone, and that hyaline cartilage is called as articular cartilage. This articular cartilage is important to keep the ends of the bone smooth for smooth movements at the synovial joint. So let us mark it here in the diagram. Maybe at this end, we can show the articular cartilage, which is the hyaline cartilage still persisting, or maybe at the other end. And this articular cartilage, which is hyaline cartilage, keeps the ends of the bone smooth for smooth movements. Now, what happens if there is aging process leading to degeneration of articular cartilage? Then it is called as osteoarthritis, and then there can be bony spicules which are called as osteophytes being formed in the elderly people. Like mostly it is seen at the level of knee joint. Now let us make this diagram ourselves and describe the process of endochondral ossification in 3 stages. One is the fetal life or intrauterine life, and then it is after birth, and finally the adult bone. Now when we are looking at the endochondral ossification, we find that in the beginning we will be having one hyaline cartilage model. So we are showing it here, the hyaline cartilage model. It is going to receive what is called as the osteogenic cells, and these osteogenic cells are brought by some blood vessels into this hyaline cartilage model. So as we draw the blood vessels, these blood vessels are bringing the osteogenic cells, and those osteogenic cells are going to form what is called as primary center of ossification. So we can mention here this primary center of ossification, which is going to form the shaft of the bone. The diaphysis of the bone is only 1 in number and is appearing in the 6 to 8 weeks of the intrauterine life. Now we can proceed further to mention that this part of the the cartilage is now turning into bone. The endochondral ossification to form the shaft of the bone. As you see after birth, the diaphysis of the bone is evident. Now, if this is the diaphysis or the shaft of the bone, what about this cartilage which is still persisting here? And what happens to the cartilage which was at the still further ends here? After birth, in that cartilage, which is growing towards the periphery, is going to receive some blood vessels, forming the secondary center of ossification. So let us show the blood vessels now. They are coming at either end. You can show it at the lower end as well. And they bring the osteogenic cells. These osteogenic cells at the ends of the bone, after birth, will be forming secondary center of ossification. And that is where we will find another part of bone is forming, which is called as the epiphysis part of the bone. The secondary centers can be more than one in number, we have mentioned earlier, contributing to epiphysis or the ends of the long bone, not only at this side but also at this side, the secondary center of ossification, which are multiple in number and forming the epiphysis. So there will be multiple epiphysis at this end and similar story for that end. But still we have got some hyaline cartilage here and at the ends of the bone. What is the nomenclature you give for that cartilage? As we see, there is some articular cartilage at the ends of the bone you can mention here at the upper end, and this articular cartilage can also be shown at the lower end. We have to understand that articular cartilage will never ossify in the life. It keep lining the ends of the bone to keep the ends of the bone smooth for smooth movements at the synovial joint. And this piece of cartilage is definitely going to get ossified, later forming the metaphysis. So this is what we are calling as the growth plate. There is one name, the growth plate, which you can show at this end as well as the other end, and this growth plate is also called as the epiphyseal plate. And this epiphyseal plate keep growing towards the ends of the bone and being replaced by the bony tissue gradually. And there comes a time when the growth of the plate is slower and the growth of the bone is faster. So ultimately the bone growth catching up with the hyaline cartilage growth, and then the growth plate is disappearing, replaced by another part of bone, which is called as metaphysis. One here at this end, one here at that end. So that will be evident in the adult bone. Let us draw the adult bone as well. So this is the adult bone, which is quite long now, and it is having the D shaft of the bone, diaphysis, and the E end of the bone, the epiphysis, multiple epiphysis at one end and multiple epiphysis on the other end. And if we are looking at the region where you had the growth plate that have been replaced by a structure bony in nature called as metaphysis. So here we mention the M for metaphysis at one end and at the other end as well. Now it is understood this is all bony tissue. All the hyaline cartilage which we were having as the fetal cartilage has been converted into bone by what is called as endochondral ossification, but still there is some hyaline cartilage persisting at the ends of the long bone, which is we are naming as the hyaline cartilage, the articular cartilage. And this articular cartilage will never ossify. It will keep the ends of the bone smooth for the smooth movements at the synovial joint. But if there is a process of osteoarthritis appearing, like during aging, then it gets degenerated and there are some bony tissue hypertrophy forming some osteophytes. The process is called as osteoarthritis, degeneration of articular cartilage. We are now going to talk about the structural details of the bone, and what we have done is taken a cut section of the bone at the mid-shaft region. As we mentioned, in the periphery, outer sheath is that of compact bone, but if we look inside the medullary cavity, there is a spongy bone or the trabeculated bone. If we talk about this trabeculation, they are formed by some rods, plates and spines we have mentioned earlier. So here, these are the trabeculated bone in the spongy component formed by rods, plates and spines. If we are coming towards the periphery, towards the compact bone, then we will have what is called as the osteons. Osteons are considered as the structural and functional unit of a compact bone, and osteons are present only in the compact bone, not in the spongy bone. So what exactly is osteon? There will be some Haversian canals, as you can see, and around these Haversian canals there are bony cells in concentric lamella. So lamellated bone, as you can can see, is a typical feature of the compact bone or the osteons. And inside the canals, which is called Haversian canal, runs the neurovascular bundle. As you notice, there will be some branches of nerve, artery, vein in the canal surrounded by the bone cells and concentric lamella. We have to understand that these blood vessels or the neurovascular bundle, if it wants to come from the outer side, say it was outside the periosteum, running longitudinally, as you can see along the long axis of the bone, it wants to enter into the bone, into the Haversian canal. The Haversian canal also run longitudinally. Then how do they reach the Haversian canal? For that, there is one other canal called Volkmann canal. So from the outside to reach the Haversian canal, we need transversely running canals called Volkmann's canal. This is one Haversian canal, another Volkmann canal reaching the deeper Haversian canal. This is how the compact bone is appearing, and this kind of a structure is missing from the trabeculated bone or the spongy bone towards the interior or towards the ends of the long bone. That is where we have the spongy bone. Let us move on to some more details. We have a magnified view of the osteon now, the structural and functional unit of the compact bone. And the osteon, which is also called as Haversian system, will have a central canal which is called as the Haversian canal. Inside this central canal or the Haversian canal run the neurovascular bundle, the nerve, artery and veins, which are important to meet with the metabolic requirement of the bone. Say for example, they will bring the oxygen and take back the CO2 or the nitrogenous waste products of the bone cells. And we have to understand that the bone is interconnected channels of different kind of spaces, like we said, central canal. From there, in all direction will be running very small canals which are called as canaliculi. So we can show very small channels going out from here. These are called as the canaliculi, as the name is suggesting, small canals. And from these canaliculi, there is a communication with some of the other spaces called as the lacunae. So you can see there is one lacuna here, another lacuna here, one more here. What exactly is a lacuna? It is basically a cave-like space which is communicating with another lacunae with the help of canaliculi. So these are intercommunicating spaces, and we have to understand why do we need these spaces. So as you can see, one lacuna connecting with other lacuna through the canaliculi. From the center, they keep on moving towards the periphery. So what exactly is inside these spaces? We have already mentioned, if we are talking about the central canal, it will have the neurovascular bundle, and from there occurs the diffusion of oxygen, other respiratory gases or nitrogenous waste products through these canaliculi. Towards the periphery will go the oxygen, and from the periphery comes back the CO2 or nitrogenous waste products. So these are some channels of communication. And then you have to mention, inside these lacunae are present the osteocytes, the cells of the bone. So this is shown here, the osteocytes which will be present in the lacuna. Lacuna we have mentioned, cave-like spaces. So one osteocyte can communicate with other osteocyte, with the next osteocyte, by sending multiple processes, and those multiple processes are passing through these canaliculi. We'll be making a diagram to understand it better, but these osteocytes, as they communicate with each other, their processes, multiple processes, they'll have cell junctions, and we know the cell junctions help a cell to create a tunnel of communication where you can have free exchange of metabolites by the process of diffusion. Then you can also see towards the exterior of the bone there will be periosteum, towards the interior there will be endosteum towards the medullary cavity, bone marrow cavity, and periosteum towards the exterior. In the periosteum there is an outer fibrous layer, inner cellular layer, and in the cellular layer you have osteogenic cells, which we have to talk about. So periosteum having two layers, outer fibrous, inner cellular, and in the inner cellular we have some osteogenic cells. Now let us draw the same diagram ourselves as well. In our diagram, we are showing one osteon here and another osteon here. As we understand, when we are talking about the compact bone, the structural and functional unit of that is the osteon, where you have a central canal, which is also called as the Haversian canal. Around that, you have concentric, lamellated, bony structure. So there will be lamellations observed here and intercommunicating channels of canals, canaliculi, and the lacunae. So we can mention intercommunicating canals, canaliculi, and the lacunae. Now let us start with the central canal, which is Haversian canal, and show that it is carrying the neurovascular bundle. Now this is the central canal in one osteon, in the other osteon, and this central canal is also called as the Haversian canal. It is having one artery as evident here, one vein, one nerve. So this artery, vein and nerve, the neurovascular bundle, how did it reach here? That has come from the outside. The same structure you can show here as well. The artery, the vein, and the nerve. In fact, they were running outside the periosteum. The periosteum having the two layers. We have mentioned there is outer fibrous layer, inner cellular layer in the periosteum, and what we are showing now is outside this periosteum, outside these two layers, you have the neurovascular bundle running in a longitudinal fashion. From there, it is running transversely to enter the central canal via communication called the Volkmann's canal. So let us show it here. The artery has come here, the vein is going from here, the nerve has entered here, from periphery towards the central canal, passing through what is called as the Volkmann's canal. And this Volkmann canal not only is connecting the outer longitudinally running neurovascular bundle towards the interior, but from one Haversian canal to the other Haversian canal also. So we are showing one more Volkmann canal here, which runs transversely. And now what we can mention is the intercommunicating channel. Like we have seen, there is a central canal. From there, multiple canaliculi are running in all directions. So this is the central canal here, and these are the canaliculi. These canaliculi are connecting the central canal with cave-like spaces, the lacunae, in concentric lamellae. So in one concentric lamella, you can mention one lacuna here, another lacuna here, one here. So intercommunicating spaces. You can draw one more lamellated structure here and mention this is the next layer of lamellation, and in this lamella, again you can see the lacuna. And how do you connect these lacunae, which are peripheral to the interior lamella? Through these small canals, the canaliculi. So we can show here the canaliculi are connecting the two lacuna. But what is the purpose of having this intercommunicating spaces? Actually, through these intercommunicating spaces only, the neurovascular bundle is meeting the metabolic requirements of the various cells in the bone by the process of diffusion. So diffusion of metabolites is occurring through these canals. Like you need oxygen, you need to send out CO2 or nitrogenous waste products. That all will be carried out through these intercommunicating canals. But where are the bone cells present? The bone cells are actually present in these lacunae. Now you can show those bone cells in this part of the diagram. And as you are telling, these are the osteocytes having multiple peripheral processes. So we have shown one of the osteocyte here. In fact, more than 95% of the compact bone is made up of osteocytes. And these osteocytes, they have multiple processes. They are communicating with other osteocytes with the help of these processes. Like we can show one more concentric lamella to the periphery, showing another osteocyte here with multiple processes. And now one osteocyte is sending this process to communicate with the other osteocyte. Between the two processes, you have got what is called as cell junctions. And these cell junctions, they are important for the process of diffusion of the metabolites between the individual cells. So in this diagram, we are showing the osteocytes. But where are they present? They are actually present in these lacunae. So one osteocyte here, another osteocyte here. How do they communicate? You can show it yourself. This is one osteocyte having multiple processes, another osteocyte having multiple processes. As you zoom, if you want to communicate with the next osteocyte, then you have to use what is called as the canaliculi. So one osteocyte here, another osteocyte here. What is there in the canaliculi are the processes of osteocytes communicating with each other through the cell junctions for diffusion of metabolic products. So as you see, these canaliculi are helping us to carry not only the processes of the osteocytes, but also for diffusion purpose. This is the incoming channel, this is the outgoing channel, or vice versa. So this is the arrangement of an osteon. And we mentioned that 95% of the bone cells are the osteocytes. But then there are other cell types also, which we have to talk about. And we also need to talk about the various fibers which are present in the bone, the ground substance in the bone, the calcification in the bone. So let us look at the structure of the bone in entirety. As we discuss the composition of the bone, we have to understand bone has organic as well as inorganic component. First, we'll focus upon the organic component. There will be some cells and there is the matrix in which the cells are located. We'll be discussing 4 types of cells in the bone, and when it comes to the matrix will have some ground substance and the fibers. Fibers, when we talk about the bone, mostly it will be type 1 collagen fibers, which are basically giving us the tensile strength to the bone. And what about the ground substance? In the ground substance, we have got the proteoglycans and the glycoproteins. Now, when we are talking about the proteoglycans, we have several components, 2 of which we have to remember: the chondroitin sulfate and the keratan sulfate, coming as MCQs. And when it comes to the glycoproteins, we should remember some of the proteins like the osteocalcin and osteonectin. Now, this is the organic component of the bone. We also understand that the matrix is getting mineralized and there will be some hydroxyapatite crystals as well. So when we are talking about the mineralization and the hydroxyapatite crystals, what are the components here? Chiefly 3 names you can mention: the hydroxyl ion, the calcium, and the phosphate ion, the chief component of bone mineralization. Now let us move on to the different type of cells in the bone. The very first name we have to take is, always start embryologically, the osteoprogenitor cell. This osteoprogenitor cell is basically a stem cell, a pluripotent cell which can form other type of cells. Like which one? Like it is forming the osteoblast. Osteoblast is involved in bone formation, basically the organic component, what is called as the osteoid, the organic bone. But this organic bone component gets calcified, mineralized, trapping the osteoblast in its lacuna and converting it into what is called as the osteocyte. The osteocytes are basically older version of the osteoblast trapped in the lacuna, and they have the function of bone maintenance. When you say bone maintenance, it means it will be taking care of the metabolic requirement of the various cells and also taking care of the calcium and phosphate component of the bone. You cannot have excess of calcium in the bone and not even the deficiency. For that, we'll need some involvement of the hormones we'll be talking about: parathyroid hormone, thyrocalcitonin hormone. But at the moment, remember, most of the area in the bone is occupied by osteocytes. They are 95% in population. Now, if osteocytes are 95%, then what about osteoblast? They are 5%. Then what about the osteoprogenitor cells? The osteoprogenitor cells are very few in number, less than 1%, and so are the 4th number cell, which is called as osteoclast. They are very few in number. This osteoclast is basically not a bone cell. It has formed by the modification of blood cells coming from the bone marrow. So we have to talk about all the 4 cell types in detail, looking at their shape and structure and the function in the next coming diagram. And we should remember, more than 90% of the blood calcium in our body is actually present in the bone. So you can mention here, more than 90% is stored in the bone itself. This is the diagram where we can see the 4 type of bone cells, and we can start with the very first, which is embryologically important, the osteoprogenitor cell. This osteoprogenitor cell can be seen towards the exterior, that is towards the periosteum side, or towards the interior, that is endosteal side, towards the bone marrow cavity, the medullary cavity. Now, let us zoom this area to discuss more detail about the osteoprogenitor cell. It is a stem cell, a pluripotent cell, and it can form several other type of cells, like it is now growing and forming what is called as the osteoblast cells. So here is the osteoprogenitor cell working like a stem cell, pluripotent cell, and now converting itself into osteoblast. Now, what are the details of osteoblast? Osteoblast is a cell which is about 5% of the total population in the bone, and this is one young cell which is involved in formation of the organic matrix, which is the osteoid. So, as you can see, osteoblast is going to form the osteoid, and it is quite young, immature cell involved in secretion formation of the organic matrix, which is later going to be mineralized. And once the matrix is mineralized, then the osteoblast will be trapped inside the lacuna and its name is changed. We start calling it as the osteocyte. Let us look at the osteocytes as well now. As we zoom out, we find that 5% of the population in the bone cells are actually the osteocytes, the older version of the osteoblast. So how do you identify the osteocytes? Osteocytes are actually mature cells, a bit smaller as compared with the osteoblast, and they are having multiple processes. Those multiple processes, they need to communicate with other osteocytes, and these processes are actually running through what is called as the small canals or canaliculi. So what is the function of osteocyte? Osteocyte is for maintenance of the bone. We have to remember the osteoblast is involved in formation of bone. As we have seen, it was forming the organic matrix. When it becomes older, it is named as osteocyte, and then it is involved in maintenance of bone. To meet with the metabolic requirements like oxygen, CO2, nitrogenous waste product exchange, plus the calcium phosphate homeostasis also. Now, how does it maintain that? We will discuss. But before that, we can also talk about this osteoclast cell. Osteoclast cell is not a bone cell. It is actually a monocyte series cell coming from the bone marrow, and several monocytes, they come together to form a giant cell, a multinucleated cell called as the osteoclast. So as we see, osteoclast is actually multinucleated cell and is formed by the fusion of several monocytes. Now this osteoclast is having several hydrolytic enzymes and which can dissolve the bone matrix. It is a cell for bone resorption. But why do you need the bone resorption? Say for example, there was a fracture. At one place you need bone formation, at other place you need bone resorption. Even in the growing bone, at one place there is bone formation, at other place there is bone resorption for the remodeling of the bone. Plus, it is also helping us in calcium phosphate homeostasis. It can cause resorption of the bone and release the calcium and phosphate into the blood. But why do you need calcium and phosphate in the blood? Say, sometimes there can be situations when you have less of calcium in blood. That time we have to talk about the hormones like parathyroid hormone. Behind the thyroid gland, we have the parathyroid hormones, and they will help us in increasing the blood calcium. So how parathyroid hormone is helping us in increasing the blood calcium? Actually, we have got receptors for the parathyroid hormone on the osteocyte, and the osteocytes are then activating the osteoclast cell for bone resorption. The osteoclast will then release the calcium from the bone into the blood circulation, and hence there will be more of calcium in the blood. Plus, parathyroid hormone is also working upon the kidneys, preventing the excretion of calcium. It also works on the intestine to increase the absorption of calcium. So effectively, working at the bone level, at the kidney level, at the intestine level, it is increasing the blood calcium. Then which hormone is working for reducing the blood calcium? In the thyroid gland, you have parafollicular C cells, thyrocalcitonin hormone. So how is thyrocalcitonin hormone working? The thyrocalcitonin hormone is going to reduce the blood calcium. Yes, but how? Working in exactly the opposite fashion. The thyrocalcitonin will be reducing the activity of osteoclast cell so that more of calcium stays in the bone. Plus, it is working on the intestine and the kidneys so as to reduce the blood calcium level. They are working antagonistically with each other. So this calcium and phosphate homeostasis has to be maintained, and the osteocyte has a greater role in doing that, especially by controlling the activity of osteoclast cells. Osteoclast cells do not have receptors for parathyroid hormone. The receptors for parathyroid hormone is on the osteocyte, so it is indirect way of controlling the osteoclast. And osteoclast cells can be identified by having a ruffled cell border and its location in Howship's lacuna. You can mention here this cell is present in Howship's lacunae and it is having ruffled cell border. As you can notice, this end of the cell showing the ruffled cell border. These are some of the MCQs they are asking us. Now let us make a table to compare the characteristic feature of bone in relation to the cartilage tissue. We are making a table where we are going to compare the cartilage with the bone in terms of features like the composition and the various cell types, the fibers, the mineralization, the neurovascularity. So as we start with the cell types, we have seen in the cartilage, what we are having will be the chondrocytes in the lacuna. If we are talking about the bone, then it is the osteocytes in the lacuna. Now, coming to the matrix, in the ground substance, there are proteoglycans and the glycoproteins. And in the proteoglycans, we have to remember certain names like sulfated chondroitin and the keratan. So here, chondroitin sulfate and the keratan sulfate, whereas for the glycoproteins, you can name chondrocalcin and chondronectin. Now, what about the components in the bone? As we mentioned, it is almost similar with some differences. When we are talking about the ground substance in the bone, again, we are having the proteoglycans and the glycoproteins. And in the proteoglycans, we need to mention the same chondroitin sulfate, keratan sulfate. But in glycoproteins, you have to change the name now. You have to mention osteocalcin and the osteonectin. In the cartilage, it is called as chondro. In the bone, it is called as the osteo. Now, what about the mineralization? When we talk about the mineralization, cartilage has no such thing. But in the bone, we have hydroxyapatite crystals, where you have to mention the hydroxyl ion, calcium ion, the phosphate ion. And this mineralization of the bone is the factor which gives hardness to the bone, strength to the bone. Cartilage is more of hydrated structure and more flexible structure. Then what about the fibers? When we talk about the fibers, in the cartilage, we have mostly type 2 collagen fibers predominantly, whereas if we are talking about the bone, it is type 1 collagen predominantly. Now here we have to be careful because there is one cartilage which is called as fibrocartilage. It is atypical cartilage. And why would you say fibrocartilage is atypical cartilage? Because it is behaving like bone and less like that of cartilage. Which feature of bone it is having? Fibrocartilage has less of type 2 collagen and it is having more of type 1 collagen, plus it is having neurovascular bundle also, just like bone. So we can mention why the fibrocartilage is atypical, because predominantly it has type 1 collagen fibers and it is also having neurovascular bundle, just like bone. You can mention here that when it comes to neurovascularity, the cartilage is having no such thing. It is present in bone. So neurovascularity is absent in the cartilage. You have nerves, vessels missing. If you cut the cartilage, there will be no bleeding, no pain, but that is not the case with the bone. And one more thing, when it comes to bone fracture and the bone is healing, the callus formation in the beginning, what form is the fibrocartilage? It is forming the woven bone. So when there is a bone fracture, the callus formation, there is a woven bone. It is made up of the fibrocartilage. Later it will change into the compact bone and the fracture will be healed. So fibrocartilage is having features very much similar to that of bone. In fact, you can write here, this table is more specific for the other type of cartilage, that is the hyaline and elastic cartilage. So it can be mentioned here because fibrocartilage is atypical. Plus, as we were talking about healing, when it comes to the cartilage, their regenerative capacity is very low. As we can mention, the regeneration is very low. Once a cartilage is compromised, the healing is very slow or it may not heal at all. But that is not the case with the bone. Bones, they heal quite well. As we know, at least in the young people, the healing is excellent. So these were some of the comparative features between the cartilage and the bone tissue.